All right, so let's take a look at the warm-up. So the warm-up is about integration. We're reviewing some integration techniques. So if you preview the content for today, you're seeing that some integration is going to be necessary due to separation of variables. And so one of the questions I've already been receiving is, quiz is an exam. What kind of integration are we able to do? And we kind of talked about that the other day. I'm not going to put nasty stuff on there. You probably won't see any trig substitution or partial fractions, but there are core integration skills that you will need to be able to use in this course. And so these are 3 examples of integrals you might see on a quiz or an exam that I feel like you should be able to do and do relatively quickly as well. So as we go through these, you're saying, boy, those are challenging. It just means you got to go review Calc 2 a little bit. You got to go do some reps in Calc 2. All right, let's take the first one. And the reason I chose these 3 is because it really models a good approach for a general integral. As you approach an integral, the first thing you should say is, can I simplify this integral? And so I look at this one and say, I can simplify that integrand as a fraction. I can rewrite this as the integral of the square root of x over x minus x cubed over x. That should simplify to x to the negative 1/2 power minus x squared. And I've simplified it, and now it's a much easier integral to do. Now I integrate the first piece, power rule. I go raise the exponent by 1, divide by 1/2, which is the same thing as multiplying by 2. Minus x cubed over 3 plus my constant. Then we look at the next one. Same thing. Can I simplify anything? I really can't here. I have the product of a t and e to the t. Really no simplification I can do here. The next thing I look for is u substitution. Can I let u equal something? Well, how do I look for u substitution? I'm looking for an inside function whose derivative is a factor. Well, the only thing that kind of pops out as an inside function to me would be the exponent of the e here, e to the t. The derivative of that is just 1. It doesn't account for the extra factor of t. So it doesn't look like substitution is the right tool here. Next I would look at, is it going to be integration by parts, trig substitution, partial fractions? It doesn't look like a partial fraction. It doesn't look like a trig sub. I'm kind of left with integration by parts. So I let u equal t, and just t, because what I'm going to do is I'm going to factor out that 3/4 there. Let u equal t, then du would be the derivative of t, which is 1 times dt. I'm going to let dv equal the rest of that integrand, which is e to the t dt. I integrate to find v. V should be e to the t. And then my formula goes uv minus the integral of v du. So I have u times v, which is t to the t minus the integral of v du, e to the t dt. 3/4 t e to the t minus 3/4 the integral of this guy, which is e to the t, plus my constant. And the last one. Once again, can I simplify anything here? There's really no algebraic simplification that I see. Next, I look for a u substitution. Here, I see that this inside function, right, it's the composition of functions here, so I have the derivative of x squared is something like x, that extra factor. It's off by a constant. I don't care about a constant factor, though. So I'm going to let u equal x squared. And then du would be the derivative dx. Derivative times dx. That's the differential. Okay? Now, once again, I have my 3/4, which I could just factor out. And I have e to the u now instead of x squared. And the other piece is x dx. That's the other piece that's left. So I'm going to take this expression and just solve it for x dx. I do that by dividing by that 2. I replace the x dx by 1/2 du. Simplify the fraction, do the integral, and lastly just replace the u with what it's equal to in terms of x and add my constant. All right. Questions? Okay. That's where I need you to be for integration. Okay. So if that's a struggle, just chunk out a certain amount of time every week to go through and do integration review, right? Look on YouTube, search integration by parts, integration by substitution. It'll be 100 videos of each, right? And then just go back to your old calculus book, right? Chapter 7, Calc Review, and just work through some problems, right? If you get stuck on a couple, you know, Mathematica will show you the steps of these. There's other programs that will show you the steps of integration. There's lots of resources out there, and make sure you're spending the time to do a review of integration. All right. Plan for today. Do a quick finish up of Euler's method. We want to talk about the error. We talked a little bit about that at the end. I want to finalize that, and then we'll get into integration by separation of variables. If you were here right away at the beginning, you saw there was a little recording popping up here. I had some questions if I could record the lecture. I will try to do that. It's just going to pick up my audio, so if I get up and walk over here and point on the board, you'll hear my audio fade out. It's not a replacement for coming to class. Trust me, if you think I'm boring in person, try watching the video, right? It will be worse, okay? So, but I will try to post that sometime later in the day, so it's a resource if you forget something or miss something. Okay, other administrative notes. All right, did everybody finish the pre-lecture? No, because I didn't post one in time. So I apologize for that. I will get better as we continue on the semester. So I will try to get those out ahead of time and keep trying to work on those. So I apologize, there was no pre-lecture for separation of variables. All right, any questions? All right. Performance of Euler's. This is where we finished off last time. We were talking about how things converge. We talked about what we remembered from numerical integration, where we had different convergence rates for the different techniques. Left and right converged at a rate proportional to 1 over n. Mid and trap did better. They converged at a rate of 1 over n squared. And Simpson's rule was awesome. That converged at a rate of 1 over n to the 4th power, right? And that idea of the error being proportional to 1 over n just meant that error was equal to some constant times 1 over n. And if you just took Calc 2 out of our new textbook, they really gave you the full formula. Right? There was like a k in there, and there was a b minus a raised to a power, and some other weird factor in the denominator. But all that stuff is just wrapped up into one constant, so we can get really the understanding of what's happening. Right? The error is equal to some constant times 1 over n. As n increases, error decreases. So what was the rate that Euler's converges at? And we said last time that it converges, that the error is proportional to 1 over n. But your book will write it a little bit differently. They're really thinking about it in terms of being related or proportional to delta t, our step size. In fact, they'll write it like kind of the absolute value of some error term is equal to, and they'll use capital O of t, converges the rate of big O of t, delta t, delta t. And that big O basically means the order of delta t, right? And so you might see something like big O of delta t or big O of delta t squared or something like that. And we'll talk more about this a little bit later in the course. But is it proportional to 1 over n or delta t? Well, actually, they're the same, really, right? Because delta t is just some number divided by n, right? It's the interval width divided by the number of steps, right? So they're basically the same, right? They're only a constant difference, and proportionality, we're scaling by constant anyway, right? And so both of those relationships should make sense. Okay, so proportional means that the error is equal to some constant now times our step size. And once again, we can look at that and say, as delta t gets bigger, error gets bigger. Delta t gets smaller, error gets smaller. That's great to know. And it makes sense if we use a smaller step size, we should be more accurate. We're checking the derivative value more often. But it actually tells us more than that. I'm just going to take that equation, divide both sides by 2. I get an expression that looks like this. And when I'm kind of thinking about that way, it tells me that if I reduce my step size by a factor of 2, if I cut my step size in half, what does it do to my error? It cuts it in half, right? And so it really gives me that relationship. If I have the step size, I have the error, right? If I cut it by a third, the step size, I cut the error by a third. And I have that relationship that I can actually compute. Okay? And the same thing is really true with our other proportionality. If it's proportional to 1 over n, then same thing, let's divide this one by 3. If I divide the other side by 3, I'll get this thing. And that basically says that if I triple the number of steps, I reduce the error by a factor of 3, right? I take a third of the error. Any questions about that relationship? All right, well, let's see if you got it then. All right, so I have some IVP, not some IVD. That's there. I got some initial value problem, whatever it is. I'm working on it. I'm trying to figure out what y of 2 is. I use Euler's. I put in 10 steps, and I find out that the error in my y of 2 approximation is 1/2. Error of 0.5, whatever that value is, plus or minus 0.5. So that's not good enough. So instead, I crank up the number of steps to 20. My new error becomes all right. See where we get to, 120. All right, 120. Oh, and more. All right. Everybody says B. That is correct. What are we doing? We're doubling the number of steps, so we need to cut the error in half. I take 1/2 divided by 1/2, I get my 1/4. Wonderful. Next one. All right, getting pretty close here. Looks like pretty happy with C, but definitely some D's and E's. How am I changing the step size? I'm going from 0.4 to 0.1. By what factor am I changing that by? Fourth, taking a fourth of that, so I need to take a fourth of my error. So I take 1/4 of 1/2, I get 1/8. That should be C. Any questions? Seems like it makes sense, right? We can calculate that. Those questions should also, however, seem stupid, right? Because what are we doing here? If I know the exact error is 1/2, then I'm going to try to improve my approximation. If you know the exact error, you know the exact solution, right? So it seems not very intelligent to try to improve our approximation. So how do we actually use this idea of scaling here? Let me just kind of model it real quickly here. This would be maybe a more realistic example. I have some differential equation, dy dx equals 2 minus y. Some initial condition. I'm using Euler's to approximate y of 2. Wonderful. I think maybe I even got it over here somewhere. Sure. So I used n equals 10, I guess. Run that guy. Run my picture. That's me approximating the differential equation using 10 steps. And I'll have some value at the end, right? If I wanted to show the points here. And I want to put a decimal in. All right. Y of 2 might be 1.785, whatever that is, right? Now, do I know the exact error? I don't. So I really don't know as I increase n how it's going to change my error because I don't know what the exact error is. But either by looking at that graph or by looking at that differential equation, something jumps out at me. It's autonomous, absolutely. It's an autonomous differential equation. So autonomous differential equation, I start looking for equilibrium solutions. What is the equilibrium solution here? 2, y equals 2. And I can kind of see that on my graph. It looks like there's a straight line solution right there. right? So can my solution that I found, the one that goes through 0, 0, can that go above 2? It can't. So I know the exact value here is bounded above by 2. I have an approximation of 1.785, right? It can't go any higher than 2, so that gives me a little bit of bound there. What about a lower bound? Well, what I could do is I could increase this by a little bit, like go from 10 to 20, and get a new value here. And the idea is the more steps I should use, the closer I'm getting towards the exact value. And so if that value increased, the previous value should be a lower bound. Okay? I can put those two things together and say, well, the lower bound is much tighter than the bigger bound, so I'm going to use the bigger bound. The error in this approximation has to be less than 0.25. That is by far the biggest the error could be. I expect it to be much less, but I can say very confidently the error is less than 0.25. Right? So I use n equals 10. I know the error is less than 0.25. Now I know if I crank up n by a certain much, I can guarantee my error to be less than a certain value. So we do the same thing we did in that clicker question. It's just we're not going to use exact error. We're going to use an error bound. Okay? And so will we be using probably too many steps? Sure. But I'll be very confident. And I can say I can use 1,000 steps. I will be 100% sure my error is less than this number. And that's the useful thing. Okay. We understand the process there, kind of the vision. Wonderful. All right. That's really all I wanted to wrap up with numerical integration. Now we want to move into 1.3 on separation of variables. All right. So in any text, anybody who teaches from a text, there'll be some things they like about the text, some things they don't like about the text. That's even the case if you're co-writing the text, right? We all kind of have a different approach to these problems and a different writing style, and some things have to be in a text. They don't necessarily have to be in a lesson. So one thing I really love about the way this section is written is this starting point here. It talks about the general approaches to differential equations. We're going to learn a bunch of different techniques to solve differential equations. But if you step back and look at them as a whole, they fall into these two groups. And stepping back and seeing this big picture is a good idea. So I want to just kind of put this in the back of your head here. All the techniques we're going to learn are basically going to fit into one of these two categories. We're either going to transform the differential equation into a form that can be directly integrated, or we're going to guess. Right? Sounds pretty bad, but it's actually not that bad. We're going to take an educated guess at the form of the solution and use analytic techniques to fill in the gaps. But that's essentially it. We're going to guess a starting point and build from it, or we're going to manipulate the differential equation until we can straight integrate it. Now, the technique we're going to learn today is separation of variables. That's going to fit into that first category. So, we have a new technique, and we will learn other techniques. We want to kind of approach our techniques from the same general structure. How do we do it? We'll learn the formal technique for using the process, but then also when are we going to use it? Because right now, if I say solve the differential equation, you're going to use separation of variables, because it's the only technique you have pretty much, analytic technique. But later on, we're going to add a couple more, and then you get to choose which technique to apply to a given differential equation. So we'll talk about how do we use it, when can we use it, and then the tips, the tricks, the warnings, we don't make the common mistakes. All right. How? How do we do this? This is the thing that I don't like about the text so much. They really go through the formal process, which you have to do in the textbook. I'm going to give you the down and dirty version. Okay? Think about this first. I have dy dt equals, and I want to use the same one that's in my notes here, t squared. Can we solve that differential equation without separation of variables? What do? We integrate it, right? We just integrate both sides to t. We're all set. No problem. However, if we change it to be this, now there's a problem. The problem is we got t's and y's over on that right-hand side. I can't just integrate that right-hand side with respect to t, because I got the t's and the y's over there. Okay? Separation of variables says put the y's over here, put the t's over here. So all I'm going to do is I'm going to divide by y. I divide by y, I get this. I'm going to multiply through by dt. I'm going to get this. I'm going to integrate. Little integral symbols. Okay. On the left-hand side, I get the natural log of the absolute value of y. On the right-hand side, I get t cubed over 3 plus some constant. At its core, that's what separation of variables is. Okay, what are the steps? You put the t's over here, you put the y's over here, you integrate, solve for the dependent variable. That's it. So, that's all there is to it. Why does the text take so long kind of to develop it? Well, I'm being pretty sloppy here, right? dy dt is the derivative of y with respect to t. It is the notation for the derivative. But what I'm doing here is I'm multiplying by dt. I'm treating it like a fraction with a numerator and a denominator. That's not actually true. However, we have the analysis to say that we can treat it like that, okay? There is more formal process that will justify us thinking about it like that. And your book will say that that's one of the beauties of the Leibniz notation, is it separates it so we can view it in that form, and then we have the analysis to justify treating it that way, okay? So, right, it's a little hand wavy. We can think about this and do it real quick, but you should know there's a little more background there to justify those steps. Okay. Questions so far? Yep. Excellent question. I did two integrals. There should be two constants, right? I should have constant over here as well, constant 2. And so I'm going to put that there. And then my next step is I'm going to subtract constant 2 to the other side. Oops. And then my next step, if I can get rid of some of that, is to look at C1 minus C2 and say, that's still going to be some new constant. I will call that constant C3. And I basically get to my same spot, okay? So really, I am adding a constant on both sides. I'm just merging those constants together to be one constant. And I will do that every time. So then I'm really lazy, and I'm just going to write one of them from now on. There will be other techniques where we won't even add constants, okay? And you should ask that same question every single time, because we always need to understand, wait a second, we're not adding a constant? I got killed in Calc 2 and I didn't add those constants, right? So they should be there. In every case where we don't use them, we can justify the same idea here, where basically that constant will eventually get swallowed up by other constants, okay? But it's good to look and ask that question. Okay, other questions? Okay, so that first step to about here, putting the t's on one side, that's really the differential equation stuff. That's our differential equation mechanics for separation of variables. This, that's really Calc 2 stuff. This, that's really algebra stuff. Guess what gives us the most problems? The last two, right? It's Calc 2 and algebra that make this process challenging. It's making little mistakes along the way or getting stuck on the integrals. That's the part that's going to make this challenging. The differential equations piece usually isn't too bad. Case in point, let's look at some here. The integration wasn't too bad, but you got to add those absolute value signs. It is incorrect if you don't. Can't just drop those guys. But now, how do we solve this guy for y? Exponential of both sides, right? I do the left-hand side is e raised to the natural log of that stuff. I do the same thing to the right. But on the right, I got to make sure I'm thinking about all that stuff in the exponent. All right, it's not e to the first thing plus e to the second thing. It's e raised to all that right-hand side. On the left-hand side, I can simplify that to the absolute value of y. On the right-hand side, I have e raised to the t cubed over 3 plus c3 in this case so far, I guess. I don't like having that constant up there, though. It bothers me, right? Just because it's ugly up there. So what can I do? I can break that down using my exponent rules to e raised to the t cubed over 3 times e to the constant. One of those exponential properties. Think of x squared times x cubed. If I multiply those, what do I get? x to the fifth or x to the 2 plus 3. I'm just using that property in reverse here, right? Okay. And then I say, wait a second, e is a constant. It's an ugly constant, but it's a constant. If I take a constant raised to a constant, I get a constant. So I will call that C4. There's some bad C4 joke in there. I'm not going to make it, though. I'm going to avoid that. But that's what I get here is basically a constant times e raised to the t cubed over 3. Okay. Now, what about that absolute value sign? Okay. Well, that should basically add a plus or a minus to the right-hand side. Okay. But C4 is a constant. As long as I allow that constant to be positive or negative, it's basically going to swallow up whatever sign changes there. Okay, so now I am dropping the absolute value, but I'm dropping it for good reason. And I have saved the best notation for last. I'm going to call that constant just C. Okay. And so there's my solution. The one other question I should ask is, so I know the constant can be positive, I know it can be negative. Can that constant be 0? Right? Because really, I divided by 0 to start, or divided by y to start this whole process. So really, everything I've done since then does not include y equals 0. And if that constant is 0, then y is equal to 0. So I'm going to do a mental check right now. Is y equals 0 a solution? I'm going to look back up the differential equation and say, okay, if the equation y equals 0, what's the derivative of y then? Zero, right? So you have a horizontal line, y equals 0, slope is 0. So the left-hand side would be 0. I plug it into the right-hand side, y equals 0. I also get 0. Yes, y equals 0 is a solution. All that does is kind of check that box. Now, really, y equals c, e raised to that power is the solution for any value of c, positive, negative, or 0. All right. Questions? All right. So now we know the mechanics. When can we use separation of variables? Whenever we can separate the variables. Yay! That's all we got to do. We just got to separate them. So maybe more formally, I got differential equation. Right-hand side is some function of t's and y's. If I can rewrite that into this form as the product of a bunch of t stuff and a bunch of y stuff, well, then I know I can separate because I could just divide by the h of y function. Okay? So if I can write this as the product of t's and y's in this case, then I'm in business. Then I can separate it. So now, do we actually know when that is? Let's look at some examples. And the idea here is try it. Try to separate them. So if you say yes, it's separable, on your sheet you should have them separated. All right, 108. We should be up to like 122-ish, I think, if we get all the way there. Take a look. Pretty happy. Everybody thinks that one's separable. It is separable. I can divide by y. I can have 2x dx over here. Okay, that's the only way to separate it. Does the 2 have to stay on the right-hand side? It doesn't, but I'm going to leave it there, right? Because over there, when I integrate, it's just a constant I pull out of my integral. If I divide by that extra constant, now it's in the denominator. Now I got to be kind of careful with that guy when I do the integration. So I would recommend leaving those constants on the right-hand side. Okay, next one. Let's stop this guy. Start the next one. Number 2, separable or non-separable. Little mixed. Most people think it's not separable, but still 32 think it is separable. Usually if you think it's separable, it's because you've tried something like this. Add 4y to the both sides, because you want to move the y's over here, like that, and then multiply by dx. But when you multiply by dx, you are multiplying the whole equation by dx, and that means you get an extra dx over here. All right, that kind of messes things up, okay? So that is not separable. And usually, addition or subtraction is the big sign. We need to write this as a product so we can divide by one of them. Usually, this addition or subtraction is a red flag. That's not going to be separable. 3. Is separable, right? Absolutely. A couple says no, probably because I threw them a curveball, right, and said, look for addition or subtraction. That probably means it's not separable. It usually does. However, there are cases when they are separable. When in this case, for instance, we can factor out that 2x, and then I can rewrite it as 1 plus y squared. So I can factor it to write it in this nice form. In this case, I could just divide by the quantity, 1 plus y squared, and multiply through by dx. And so sure enough, it is separable. So that one is separable. Any questions about separating the variables? All right. Now we just integrate. Right-hand side, x squared. You guys can handle the left-hand side. Actually, it's not too bad, right? It's arctangent. We had arctangent there, and we could finish that problem up. Okay. But, so when can we separate them? Whenever we can separate them, hooray! And then sad face here, right? But that doesn't guarantee we can finish the technique, okay? That doesn't necessarily mean we're going to find that unknown function and be able to write that guy out. Well, why not? Well, what's the problem here? Here we have an example. We separate the variables, no problem. Integrate both sides. Being the generous person I am, I'll integrate the left. But what about that integral on the right? What do we do with this thing on the right? Try use substitution. The derivative of that inside function, x squared, would kick out a 2x, though. That 2x is not a factor. So substitution is not going to work here, okay? And so you might say, I don't know. I do not know how to integrate this, so this would be hard for me. But maybe I just throw it into Mathematica or something, right? No. Actually, in this case, that right-hand side isn't a tough integral. It's an integral you can't do, right? Sort of. People will say you can't integrate that. Well, not technically true. You can't find a closed form antiderivative. You can't have some nice, clean antiderivative function that you're going to put in here. You've done this integral before in Calc 2 because you approximated the integrand with a Taylor series and put that in there and maybe integrated the series. That means you could express it in terms of an infinite series, but I can't have some closed form function over here. So in that sense, you can't integrate it. Okay? So that means I can't get some nice closed form clean equation for my unknown function. So that's one of the things we might run into. We can't complete the integration. What else? What other issues? So now the tips, the tricks, the warnings. A couple things here. Tip number 1, right? Integration. That's going to be the hard thing. So review integration. Do a bunch of integrals. Okay? Go through those core techniques of integration by parts and use substitution. Go on YouTube, tons of videos, right? Just review it, do some problems. The more you do, the better you're going to be. 2, check your work, right? Check your work as you go through the problems. You're going to be integrating both sides and forming your solution. So yes, you can check with your calculator because it can solve the differential equation in most cases. But check the steps, check the integrals as you go along the way, right? Also, check them by another technique, right? When I do these problems, I'll have Mathematica open on the side and have that vector plot all created, and all I have to do is go throw on the right-hand side to see the new vector field, or the new slope field. And so I can look at my function, look at the field and say, oh, that's got to be the wrong function. That doesn't fit, right? You could also throw that plot of that function on the vector field as well, like you've kind of started to do in some of the labs, and see if they match up. That's a nice way to check your work by some other technique. Make sure you check your work. And the last one, the big mistakes we make as we're going through the mechanics. Number one, make sure you bring your constant in on time. What do I mean by that? I mean, we separate the variables, we got y's over here, we got t's over here, we integrate, we do a bunch of algebra, we get to the end and say, oh, I forgot that constant. Throw it on at the end, plus c. Can't do that, right? Because along the way, that algebra might have moved that plus c around, and so it's not just some extra plus c at the end. You got to add it when you do the integration. Yep. Yep. Erf. That's right. Yep. Error function. It's a special function. It's a special function designed to represent the solution of that. So, can we integrate it and find a closed form antiderivative? No, we can't. But can we find the exact value of the integral for different intervals? Yeah, we always could. We can always use that Taylor series, show it converges to something. So in other words, I can't do this thing and go, boom, there's my function. But I can do this, I can do this, I can do this, I can do any number exactly. So in some sense, that defines a function, because at any of those values, I can find the exact value. Okay, and so we define erf, or in Mathematica, it will be like sine integral, some other thing. And the definition is the integral, it's a function of, say, t, it's the integral from 0 to t of e to the negative x squared dx. So it's kind of defined to be all of the values of that integral over any interval. Okay? Good times, right? Okay. And you might look at all that stuff and say, yeah, that's just not important to me, right? You know, e to the negative x squared is actually a really important function, right? That form is what models a normal distribution. So almost anything you're going to do with probability or statistics is going to be modeled by something like e to the negative x squared. So it really is an important thing that we are worried about, which is probably why we've defined a special function to give us the values. All right. Other questions? Good question. Okay, so make sure you bring those constant on time. The next one is be careful with the algebra. There are lots of little mistakes that we can run into. Let's talk about those by going through this problem. So here's one for you. Not a quiz, not anything you're getting a grade on. So if you don't know what to do, ask your neighbor, look at their paper, raise your hand. Get started doing something. I don't want you to be working through this. Feel free to talk. Do my phone off the walk now. Okay, and we got a mix. Talk to your neighbor. All right, let's take a look. Separate the variables. I multiply by y. I multiply by dx, in theory. I integrate both sides. I got y squared over 2. I got x squared over 2. Multiply by 2. Take the square root. I got y equals x. I add my constant. It's probably 1. That's b, right? What did I do wrong so far? I got to add my constant here. And I asked it here where I did the integration, not at the end. Okay? Now I add my constant there. Call it C1. Multiply the whole thing by 2. I got y squared equals x squared plus 2 times a constant. But 2 times a constant is just a constant. It's a different constant. I'll get a different name, but it's just a constant. So if I multiply constant by constant, I'm just going to swallow up that extra factor. Whatever. I have some constant value here. Take the square root. Y equals plus or minus the square root of x squared plus C2. Okay. Now, do I need the plus or minus? Right? If I need the plus or minus, then the answer is E, none of the above. But do I need the plus or minus? These are two separate functions. It's either got to be the plus or it's got to be the minus here, which is going to be the plus. Why? Right. So I'm having an initial condition. It gives me that positive y value. So in this case, I really can just look at the positive y as that function here. Okay. So that's what I have. I do want to find the value of C2. Now I plug in my initial condition. I got y equals 1 when x is 0. That tells me that implies that C2 is equal to 1. My solution is the square root of x squared plus 1. Okay. The other mistake I see a lot is people putting their constant on the right time, going all the way through the steps and saying, oh, but isn't this just the square root of x squared plus the square root of 1? No. No. That is a very, very common mistake. Okay? You can't distribute a square root over addition. You can't distribute a power. If you think about something like a plus b squared, is that a squared plus b squared? No, we got that weird factor in the middle, right? You can't distribute a power. Right? So make sure we're careful with that common algebraic mistake. Okay? All right. Any questions so far about this one? Yep. You just put C, it's not technically correct. Will I take points off for it? No. Right? I won't kill you for not putting subscripts. But I want you to see that they're different values, right? They really are changing. Other questions? The reason I really want to stress that is because one of the questions I get is, did you have to wait all the way to the end to find the value of C? The answer is no, right? I could have plugged it in right here, my initial condition. When y is 1 and x is 0, what is my constant? Well, that implies my constant is 1, just like I got, right? Well, can I plug it in here? Sure. Plug the initial condition here, I get 1/2 equals 0 plus constant. Is that a problem? I got a different value for my constant here. It's a different constant, right? If I find out that C1 is equal to 1/2, that's fine because I would plug in the 1/2 here. And then when I multiply the whole thing by 2, the thing here would end up to be 1. So it's all going to work out, okay? It's all going to work out. You can find your constant at any point. You just have to always treat it correctly algebraically, okay? Okay. Any questions about this problem? All right. One more topic here. Explicit solutions versus implicit solutions. What does this stuff mean? All right. Now the idea is an explicit solution. Well, first of all, what are we trying to figure out? We have a differential equation, dy dt equals some stuff, right? Equals some function of y and t. Oh boy. Our goal is to find the solution by finding y. We want to figure out what that unknown function is. Find y as a function of t. And if we can do that, that's an explicit solution. Y equals that guy. Okay? Sometimes we can't necessarily do that, as in the previous problem. Right? I got to y squared equals x squared plus some constant, but this here isn't a function. It's an equation. It's a relationship. If I plotted it, it would look probably something like this. Okay? Something to that effect. It's not a function. Why isn't it a function? Tell me about the graph and tell me why it's not a function. Fails the vertical line test. Absolutely, right? I can't just solve this for y. When we tried to, it was y equals plus or minus, right? That's really two functions, not one function. Okay? So if I have this guy, the relationship that might represent the full solution, I can just leave it like this. If I can't solve it for y as a function, you can leave it in this form. Is it still a relationship between y and x? There is, right? It's just implied that as I change x, the y value has to change. I'm not explicitly writing out y equals this guy, but the relationship is implied, and so we call this the implicit solution. Okay? So the implicit solution just means you haven't solved it for y. And there are problems where you can't solve it explicitly for y. This would be an example here. Okay? For this differential equation, right, I multiply both sides by y squared plus 1. I multiply both sides by dt. I integrate. I get y cubed over 3 plus y. I get 2/3 t cubed plus some constant. I look at that result. That is a series of integral curves. Notation the book would use. All the curves that represent the solution. But I can't solve this thing for y and say the solution is y equals this function of t. Right? But this family of curves is really the solution. Well, how do I visualize this though? Because I can't plot it. I can't look and say and plot the function here because it's this relationship. Well, one thing I can do is rewrite it like this. I've rewritten into a form that looks like this. Some function of two variables equals some constant. And if you've had calculus 3, you should recognize that expression as the level curve of some surface. Okay? And if I put specific values of a c on here, I'd have the contour lines from my contour plot. And if I wanted to do a contour plot for a function of more than one variable, I would simply have this expression and put in different values of 1 and have all those curves. Okay? Now to do a contour plot, we use a command contour plot. We put this right in here. And so it turns out if I want to plot this relationship, not a function, I can use contour plot and just put in the equation I get here. So specifically, if I use my initial condition and I plug that in, what is the value of c that I get? 0, right? C would be 0. So really this represents the specific solution. Now I want to visualize that specific solution. So what do? I go to Mathematica. I can't plot because my solution isn't a function. So instead I use contour plot and I put in the full equation. I'm just typing in that equation. I'm using a double equal sign for the equal though. And then I give it a range of t and y values and it gives me my plot. In general, this is how you plot relationships in Mathematica and other software packages as well. Okay? So if I wanted to plot a circle, for instance, I would just do y squared plus t squared equals 4. I get my circle. I can't just plot the full circle using the plot command, okay? All right. All right, for next time, complete the lab assignments. I posted some labs for next week. That is going to be your assignment for section 1.2. Are those lab assignments? I will shortly post assignment for this thing for next week, and then prep for 1.4 for Tuesday.